Let's now consider the intersection of a quadric surface with another quadric surface. Now, the sphere x squared plus y squared plus z squared equals 16 is a quadric surface. That coefficient a, b, and c of x squared, y squared, and z squared would all be 1, and the d would be 16 or negative 16 depending on which form you're referring to. And we intersect with a surface that we looked at earlier. Okay, this surface being a hyperboloid. In the xy plane, now we want to consider these two surfaces as they intersect the xy plane. So in the xy plane, what are our surfaces? Well, z equals 0. We get the equations 4x squared plus 9y squared equals 36, which is the ellipse that we've seen before, and x squared plus y squared equals 16, which is just a circle of radius 4. Now, if you recall the sketch in the xy plane, this surface would come out 3 units in the x direction, 2 units in the y direction. We would have a rectangle that looks something like this, and an ellipse inside of that rectangle. So that would be this locus. The circle, well, that's a circle of radius 4. So if we come out to 4 units in the x and 4 units on the y, and 4 units in the negative x, 4 units in the negative y direction, we get, well, we could draw, I mean, a circle is actually an ellipse where you have equal sides. We can draw the circle inside this square just as we would any other ellipse. Not particularly well drawn in the third quadrant, and not all that great in the others. But we see that this equation gives us the circle. Now we're looking at the intersection of these two surfaces, and what we're going to find then, what we see from this graph is they don't intersect in the xy plane. The ellipse is entirely inside of the circle. There's no point of crossing. Now let's look at the xz plane. In the xz plane, we have the equations y equals 0, so we have the equation 4x squared minus z squared equals 36. If we rearrange this, it's x squared over 3 squared minus z squared over 6 squared equals 1. And this tells us that we have to move up 6 units in the z direction, 6 units down, only 3 units in the x direction. We can construct our rectangle and construct our ellipse. Again, not particularly well drawn. And we can also construct our circle, just a circle of radius 4. So we have to come out 4 units here. We have to come up 4 units here. Now I haven't been consistent with my scales, so my circle is going to look a little bit like an ellipse, but this should actually be the circle. And it's going to come around like so. Again, it appears flattened because I haven't used consistent scale. But it's very clear that these two shapes do intersect. So we have 4 points of intersection in the xz plane. Okay, well, if we got x, y, and z here. This tells us that in the xz plane, at some point that we can determine later. Now this is not one of the rectangles we used to sketch. This is the rectangle that joins these 4 points, and we haven't determined the coordinates of those points, although it wouldn't be difficult to do. Whatever our surface does, it intersects the xz plane in these points. We could look at intersections with the yz plane, where we'd also have an intersection because we would again have a z squared over 6 squared. And begin to at least understand the idea that there are probably lots of points where these two surfaces intersect. Now, it's going to be difficult, tedious, and probably more challenging than we want it to be to take a bunch of planes parallel to the xz plane, a bunch of planes parallel to the yz plane, and a bunch of planes parallel to the xy plane and see where these intersections occur. So what we're going to do is we're going to do an algebraic solution, and all we need for an algebraic solution, to begin at least, is to add these two equations, which will eliminate z and tell us something important about the intersection of these surfaces.